This is the fourth installment of Advanced J1939. I've back to the circuit simulation. I've made a few changes here, added a few components. We are also back to where we have an ideal signal. So the inductors and capacitors are no longer present on my CAN line. That means our signals are going to be, they're going to look very clean. Our simulated signals that look very clean. They'll be vertical lines and horizontal lines without any other ringing. The undershoot, the overshoot, those things. Something else that I've done is I've moved the supplies around. So this node identifier, this says any place where it says 5 volts, that means that this is going to be 5 volts. Same thing here with the 2.5 volts. This lets me clean this circuit up a little bit. So you can imagine any place where this tag says 2.5 volts, it's 2.5, same for 5. I've also replaced the physical switches, the time controlled switches with a field effect transistor, a MOSFET. So these are a high side driver. This is a transistor which acts very quickly. It acts the same as a switch. The schematic or the symbol of it, you could think of this in your mind as just being a switch that is either open or closed. So it's one that acts very quickly. We have this driver which controls those high side and low side drivers, this driver chip. So this goes back to our schematic of the CAN transceiver, the block diagram. We've added these high side and low side drivers, and then some logic here is going to either cause this driver to turn these high side and low side drivers either on or off, and they would both happen at the same time because we need to provide the 5 volts and the ground at the same time. If we don't, then it's going to cause an offset on the signal, and we'll look at those as one of our failures. If a controller fails, if this driver gets damaged, and something like this can get damaged due to a lightning strike, get damaged due to some sorts of failures where I have some spike that gets into the system. So some wire-to-wire failure that might happen on CAN high or CAN low. Pretty unlikely, but it is protected. But yes, you could definitely damage this driver. Same thing with over temperature. So we might make one of these come on and the other one not come on, and that's bad on the CAN network, as we'll see for a failure. And in that case, there is no fixing this, and if that's the case, then you have to replace that controller. It's not like you can go in and fix this particular chip, at least not in the field. All right, getting back to our simulation then, taking a look at it. I also have put here a 500K hertz clock, so this is simulating 500K CAN, 500,000 bits per second. This clock is going to kind of show us where each of the transitions should occur, where we'd expect to either read a logic 1 or a logic 0. So I'll go ahead and run the simulation, and we'll see what that looks like. Takes it a couple of seconds here, and we can see that bit pattern that I wanted to put into this was a logic 0, a logic 1, a logic 1, a logic 0, a logic 1, a logic 0, and so forth. So it's just transitioning back and forth. And what we see here, we see the CAN lines go from 2.5 volts, where they're both sitting at 2.5 volts, and a difference in voltage of 0, to where there's a difference in voltage of about 2.2 volts. Similar to what you see on a robust. So here's our clock down here. You can just imagine each one of these. This is 2 microseconds, 2 millionths of a second for each bit at 500K. The 500K, we're going to expect this every 2 microseconds. We're going to read is this a high or is this a low? Is it a logic 1 or is it a logic 0? And then that would be interpreted. So this is the CAN transceiver acting as a transmitter. It's putting information out onto the CAN bus. So one of the things that's very important is that the CAN bus has to be quiet before we do that. So at this point, this isn't really what we would call a logic 1. This is just the bus being idle, and the bus has to be idle and quiet for some period of time before any controller can come in and then transmit this first bit to start the frame and say, hey, I want to take the bus and I want to put a message out on the bus. As long as nobody else has done that, then this controller has the authority or has the right to go out and to put its message on the CAN bus. Once it's finished, the CAN bus will be idle for a few microseconds, and then any other controller can use this. So one of the things that's great with CAN, so I could have some device that is really not that important. Let's say the radio. The radio is on the bus and it's putting some message out. Whatever message it puts out something that says, "Hey, here's my radio station," say for example. And yeah, that's really important. Probably not really, but it's out there putting this information on the bus. And let's say that the engine controller has a crucial message that it needs to get out. If that radio is using the CAN bus, the engine controller, for its critical message, let's say something, or from the transmission, that a shift is in progress or we're approaching a shift in progress. If we're on-road trucks, something like an ABS event is a very high priority message. For lots of machines, the engine torque speed command, what I want the engine speed and the torque of the engine to be coming from some vehicle controller or transmission controller. Those messages are critical, much more important than this radio message. But the radio is using the bus. If it's putting this message on the bus, then we have to wait until the radio is finished with that message. It's only a few microseconds, so in looking at it in time, it's not very long that this is going to occur. This is one of the great things about CAN. You can't come on to the bus and say, I've got a message that's more important than yours and you need to stop transmitting. Unless the devices start at the same exact period of time, as we'll talk about in arbitration. What that means is I've got to wait until it's finished. If it's using the bus, if it's got a valid message that it's putting on the bus, whatever the device is, that message has to finish before somebody else can use the bus. Once it's done, there'll be a period where the bus is quiet, and then that more important message or very important message can be put onto the CAN bus. So they may have to wait a few microseconds, a few millionths of a second until the bus is free. So let's take a look at a real CAN signal and kind of compare it. This is a 250K CAN signal, and I know that it's 250K because of this time period between for one bit to occur. It's 2 microseconds for 500K, 4 microseconds, just right there, it's really hard to get it, 4 microseconds exactly for 250K. So each of these is a bit. We can see that we have a 1, we have a 0, we have a 1, we have a 0, we have a 1. So similar to what we were putting on the CAN bus for our message, here's our virtual CAN bus, here's a real message. Of course, this is a real signal, so we can see that there are the effects of the inductance and the capacitance, where the energy is being stored in a capacitor in a form of an electric field, and in an inductor in a form of magnetic field. That energy release is what causes this oscillation. It causes this to bounce around somewhat. But we're really not that concerned with it because we're looking at the difference in the voltage. And so you can imagine our clock, our sampling point where we're going to sample this is going to be somewhere after we see the transition. We'll come in and we'll sample it someplace. For example, right here, we would take a look at it. It's like, what is the logic state? Is it a 0 or is it a 1 at this point? Typically, you wouldn't want to sample it out here because in this region, we know we might have some of this ringing. We're going to not look at it there. Same thing for the recessive state. We're not going to try to read it right here when we see it drop. We're going to wait a little bit and we're going to sample it out here at some point. So this is more of the error proofing of CAN. This is more of the robust, how it's and why it's so robust. So I will mention one other thing that you see here, because we have an indication of this stuffed bit. We can see that we have, get rid of the rulers here, we have a we have what's called a stuffed bit. One of the other pieces of CAN is, one of the other rules is you're not allowed to keep the bus at the same logic state for more than 5 bits in a row. So if you can see, we have 5 recessive bits in a row. The next bit was going to be a recessive bit. And so therefore, CAN causes the bus to go, the CAN transceiver is designed to cause the bus to go to the opposite state. We'll talk more about this, but that's what this meaning of the stuffed bit is. We put these bits in so that I don't have 6 of these logic 1s in a row. I only have 5. Same thing for the logic 0s. I would never have 6 of them in a row. That's a violation. I have to put one of these stuffed bits in. We'll talk more about that as part of the error proofing of CAN. but it just does contribute to that. I wanted to mention it because this does show up as a stuffed bit here. Okay, the next time we'll take a look at, we've looked at the transmission, how the CAN transceiver transmits. We'll look at how the CAN transceiver receives, because it has to receive at the same time that it's transmitting. This is more of the error proofing of CAN, something called the arbitration piece of CAN. This prevents collisions from occurring, where I'm trying to drive something to a logic 1 and a logic 0 at the same time. We can't do that. This is the CAN bus is a parallel circuit. It always has to be at the same voltage everywhere throughout the circuit. So that'll be something that we'll talk about in later episodes.